Okay, dear students, today we are going to study about a very special topic which is to be known in case of BJT is early effect. So what is meant by early effect? After knowing this, you can study, you can understand the characteristics of BJT very easily. Okay, so let us consider a PNP transistor which is connected in active region. What is meant by active region? The emitter base junction must be forward biased. So that is between emitter and base terminal, there is a junction known as a JE. And between collector and base, the junction is known as a JC. So the emitter junction must be forward biased. That is between emitter and base forward biased. That is P terminal is connected, P material is connected to positive terminal of the battery. N material is connected to negative terminal of the battery. Similarly, collector junction must be reverse biased. That is, the outer P material, collector is a P material, negative terminal of the battery, then N is connected to positive terminal of the battery. So, this is under strong reverse bias condition. Emitter junction is under strong forward bias condition. So, let us assume that the battery is named as VCC. And this is VEE because it is connected near to the emitter terminal. And you know that in case of the working of BJT, the carriers starting from the emitter terminal, they are diffused towards base due to this repulsion. Suppose the holes are positive charge carriers here, they are repelled by the positive terminal of the battery and they will try to move towards the emitter junction and they will enter into base region if the external voltage is less than this barrier voltage. So let us assume that there is a barrier here. Here across this emitter junction, there is a strong barrier. And you know that in case of a forward biased emitter junction, if the external voltage is more than this barrier voltage, the barrier width decreases. At the same time, the collector junction is reverse biased. And you know that the depletion width increases due to the external reverse bias condition. See here, as soon as this external voltage is increasing, reverse voltage is increasing, the depletion width around this junction increases. So, the depletion width is increasing in this way. And you know that the base region is very small. Emitter is space is less compared to collector and collector has a maximum area. Therefore, whenever this depletion width increases, the depletion width is increasing into the collector region and into the base region also. Initially what is the base width here? Here, this is the depletion width. Here, this is the depletion width in JE and JC junctions. Whenever this forward bias is increasing, the collector, which is reverse biased, the depletion width increases. Therefore, initially the base width is this one. Now, because of this extension of depletion width under reverse bias condition, the depletion width is come down to like this. So, the effective base width decreases due to the external reverse voltage across the collector junction. So, this is known as early effect. Okay, I am repeating again here. Whenever the collector junction is reverse biased, the depletion width near the collector junction increases on both sides. That is towards collector region and towards the base region. Therefore, the effective base width decreases. Previously, the width is very large. Now, the width is decreased to some lowest level. Okay, therefore, this effect can be studied while the CB-CECC characteristics are going to be explained. Okay, so here the strong reverse bias is existing near the collector junction. A strong forward bias is existing near the emitter junction. Okay, so the early effect is nothing but the change in the base width due to the external reverse biased collector junction. Therefore, whenever you are increasing the reverse bias across the collector junction, the effective base width decreases because see here the collector junction is reverse biased, so depletion width continuously increasing from both sides. That is towards base side and towards collector side, it is increasing. But the change can be seen effectively towards the base than at the collector, because the space, the area of the collector region is very big compared to base, because base region is very, very thin. That you know already. Therefore, whenever the collector junction, the external reverse voltage increases, the depletion width across JC increases, so that the base width is reducing. See here, the base width is slowly reducing. This is known as a early effect. Okay, then what are the consequences? Okay, so this is the emitter junction forward bias condition. This is VEE. So what are the consequences? The first consequence is collector current increases. How the collector current increases? Initially, while studying the operation of BJT, we discussed that majority of the carriers will cross the collector junction, or will enter into the collector junction via base. Okay, for example, as a number you can say, for example, 100 holes started from here, and 5% of them recombine with the base region, and 95% reach the collector. Okay, therefore 5% of recombinations takes place in the base. But due to this early effect, as the base width decreases, the recombinations are very, very less. Okay, for example, here this is 95. Due to this reduction in the base width, the reaching number, so only 2 recombinations takes place. Therefore, majority of the carriers starting from the emitter reach the collector. Therefore, initially the collector current is only 95. Now the number is increased to 98. Therefore, the collector current increases. So, due to early effect, the first consequence is towards collector side, the collector current increases. Second one, emitter current increases. What is emitter current? The holes in the emitter region increases. Already just for an example, we said it is 100. How the emitter current increases? See here, as the base width is reducing due to this expansion of depletion layer, the minority carriers in the base. What are the minority carriers in N region? Holes. So, some of the holes which are here, due to the pushing of the expansion of the depletion layer, some of the holes may jump into this P region. They are pushed towards the emitter side. So, if 2 holes come this side, 100 plus 2 will become 102. Therefore, the hole current also, that is the emitter current also increases. So, this is the second consequence. Third consequence. This is an extreme case where if you goes on increase the reverse bias, the effective base width decreases and this depletion width increases further, and finally at certain point of time, what is happening? The base width completely closed. So in that case, the base current is almost 0 and it will lead to the destruction of BJT. So that is also known as this is known as reach through, or we can also say this as a punch through effect. So these are the 3 consequences we can see after the early effects results in BJT. So these are very, very important points to be considered while you are studying the characteristics of BJT under common base, common emitter and common collector configurations. Okay, now we are going to study a very, very fundamental concepts of the characteristics of common base, common collector and common emitter configurations. Okay. Characteristics means what? Characteristics means what is the response of BJT for a particular input signals you are giving to that particular component. Okay, so before going to the study of characteristics, let us see, this is a common base configuration. Here we have shown the common base configuration for both NPN and PNP transistors. Okay, so here this is connected, both the transistors are connected in active region. So while coming to the study of characteristics, you have to give some extra inputs like extra meters, voltmeter to measure the voltage, ammeter to measure the current passing through the circuit. So here the experimental setup circuit is different compared to the configuration. So here the default thing is the emitter base junction is a forward bias. See, this is a NPN transistor. This is NPN transistor. So N negative, P positive. This is perfectly under forward bias condition. And collector junction is reverse biased. So this is N material. N is connected to positive and P is connected to negative. So this is under perfect active region. Similarly, PNP transistor is also under perfect active region. See here, this is a PNP transistor. How do you know this? See here, the arrow is from emitter to base. The direction of Hole's movement is from emitter to the base. See here, this emitter base junction is forward biased. P positive, N negative. So this is under forward bias condition. Collector junction is reverse biased. That is, collector material is P. So P negative, N positive. So this is under reverse bias condition only. So the default operating region is active region only. So what is the purpose of connecting the BJT in active region? For amplification. So to amplify any weak signals, to raise the magnitude of any weak signals, we must connect BJT in any configuration in active region only. So both transistors are under active region. Now we are going to study the characteristics. That is, for a common base configuration, we are going to study the characteristics. So the characteristics are mainly divided into two types. One characteristic is towards the input side, another one is towards the output side. So input is what? For example, if you take this NPN transistor under common base configuration, common base means this is a base terminal. Here the base is grounded, or it may be common to any supply. It has two meanings. Similarly, PNP transistor is under common base configuration. That is, here this is a base terminal. The base is either ground or connected to any supply. Okay, so this is about the base connection, and this is about the base connection. Okay, now input characteristics means what? See, input means if you draw any graph between the input voltage and input current, that is known as the input characteristics. But while doing input characteristics, the output must be kept constant. Output condition should not be changed. Then only we can take the characteristics for different values of voltage and current. Similarly, output characteristics means the graph drawn by taking voltages and currents by keeping input constant. So while doing output characteristics, input should not be changed. So now the experimental setup circuit is different from this normal configuration. So what is the input voltage here? Between, this is emitter terminal, between emitter and base, 1 voltmeter you are going to connect, VEB, and the corresponding current can be noted by using ammeter, IE. Similarly, what is the output voltage we can connect? Between collector and base. So this is a collector terminal. Between collector and base, 1 voltmeter to measure the output voltage, and output current is nothing but the ammeter. So 2 voltmeters, 2 ammeters we will connect across the BJT. Therefore, now we are going to connect BJT with an experimental setup to study the characteristics. Okay, this is an experimental setup for common base to study the input and output characteristics. See here, this is a common base configuration. So usually in your lab you will use BC107. Okay, so this is a NPN transistor, NPN transistor. See here, between emitter and base you are giving a forward bias connections because this is an N material, N negative and then P positive. So this is perfectly under forward bias condition. Collector junction is reverse biased. Collector material is N, so reverse means N positive and P negative. So this is under reverse biased condition. Okay, so here the common base configuration means the base is grounded. See, completely the base terminal is perfectly under ground condition. Now we have connected the voltmeter between emitter and base, a voltmeter. That's why it is known as VEB, and the emitter current, that is ammeter. So usually we will connect here a milliammeter. Okay, usually 0 to 200 milliammeter we will connect. Then output also, to measure the output voltage and output currents, we will connect a voltmeter between collector and base. That's why this is known as VCB. And to measure the collector current, we will connect an ammeter, that is collector current. So which is measured in milliamperes. Okay, so in order to show the external supply as a practical voltage source, we are connecting voltage with a series resistance and here also a voltage with a series resistance, because the signal should not enter directly into the BJT. Just to protect them, we are using some small resistances. Okay, therefore here this is known as the experimental setup of BJT. Now we are going to study the characteristics. So what is meant by input characteristics from this circuit? So input characteristics are this: between input voltage and input current. We are going to study the input characteristics. So how to define input characteristics? So they are defined as the graph which is drawn, or the characteristic curves drawn by taking VEB on x-axis and IE on y-axis by keeping VCB constant. If you put the output voltage constant, the input voltage and currents can be taken effectively. So the output voltage must be kept constant while doing input characteristics. So that is known as input characteristic. See here. So what is taken here? On x-axis VEB and on y-axis IE. So how to define input characteristics here? By taking VEB on x-axis, IE on y-axis by keeping VCB constant. See here what we have done here. Emitter base voltage VEB, which is taken on x-axis, and IE, which is measured in milliampere. So this is known as emitter current, which is measured in milliamperes, which is taken on y-axis by keeping VCB constant. VCB, where it is connected? See here. This is VCB, which is kept constant. That means initially kept VCB at 0 volts. Then you keep VCB at 10 volts and VCB at 20 volts. As the reverse bias connection is given there, we are mentioning this as a minus voltage, minus 10, minus 20. See how the characteristics are changing here. The characteristic curves are changing like this. Initially when VCB is equal to 0, here the current is raised like this at this point. Okay, then here again when VCB is minus 10 volts, the current rises sharply at this point. When VCB is equal to minus 20, the current rises sharply in advance. For example, if this is some 0.5 and this is a 0.4 and this is a 0.3 and so on. Okay, see here what is happening here. Whenever the collector voltage is increasing, as soon as the reverse voltage is increasing, it is conducting earlier than the previous one. So this is completely due to early effect. So already you know that whenever the collector junction is more reverse biased, the effective base width decreases. Okay, therefore here what is happening here, if you see the characteristics curve, as the depletion width is decreasing slowly, that is the voltage between emitter and base decreases. So as the space, so if you see here between emitter and base, the base width decreases, means there is a very even the small voltage for conduction. Therefore the curve is advances. So okay, it's come forward because it conducts early, because due to early effect. So that's why the characteristic curves are like this. So it conducts earlier whenever you are increasing the reverse voltage due to effective base width decreases. Okay, now let us see the output characteristics of common base configuration by taking VCB on x-axis and IC on y-axis by keeping IE constant. So in the previous diagram we say, see here this IE is kept constant. Suppose if IE is, it can vary from the maximum voltage ranging is 0 to 200 milliamperes. Here we are giving different IE. IE is equal to 0 milli, IE is equal to 5 milli, IE is equal to 10 milliamperes. Like that you can change IE in different steps and each step must be the control emitter current for taking output characteristic curves. Okay, see here. VCB on x-axis, IC y-axis and IE is kept constant. So when IE is equal to 0 milliamperes, then automatically when IE is equal to 0 and there is no flow of charge carriers from emitter, collector current is also 0. Therefore, this is when IE is equal to 0, the curve is very, very close to x-axis, that is the collector current is almost 0. But when the emitter current is increased to 5 milliamperes, see here, this is 5 milliamperes. Then when IE is equal to 5 milliamperes, according to this diagram, see here, according to the BJT operation, suppose if 100 carriers started at the emitter, very few recombine in the base, remaining reach the collector. Suppose if 100 carriers started here, 5 recombine in the base, 95 should reach the collector. That is, the collector current is always less than emitter current because IE is equal to IB plus IC. So this is known as a transistor current equation. IE is equal to IB plus IC. Very few charge carriers recombine in the base. Therefore, when IB is taken, IE must be equal to IC if IB is equal to 0. If there are no recombinations takes place like in ideal transistor, IE is equal to IC. But in practically, certain recombinations takes place within the base. Therefore, always IC is less than IE because some recombinations takes place within the base. Therefore, if you see the characteristics of this common base configuration, when emitter current is 5 milliamperes, what is the collector current? The curve is below this one. Similarly, when emitter current is 10 milliamperes, see here, this is 10 milliamperes, the collector current is this one. Isn't it? Then, when emitter current is 15 milliamperes, see here, this is 15 milliamperes, collector current is just below that. Therefore, if you extend this line, you can see the positive changes. Because VCB is negative, so when collector voltage and collector current are negative, that's why we have taken on the same axis, on the positive axis. If you extend towards the back side, you can see some positive VCB values. Okay, similarly, when IE is equal to 20 milliamperes, IC is less than that, around 18 or 19 milliamperes. Similarly, like this, if IE, emitter current is 25 milliamperes, IC is almost below that value. See, all these shaded dark lines are the collector current, which is always less than the emitter current. That's why common base configuration characteristic curves are, output characteristics are parallel to x-axis. So in examination point of view also, they will ask why the common base output characteristics are parallel towards the voltage axis. The reason is IE is equal to IC. If it is an ideal case, therefore, if it is a 5, it is less than 5. If it is 10, less than 10, like that. Okay, which you are keeping constant? IE is keep constant. Okay, now the another important concept we need to study from this common base configuration is you have to mark the operating regions. Already we studied what is meant by active region, what is meant by saturation region, what is meant by cutoff region. So the important regions are already marked on the graph. If you see, first of all, tell me what is meant by cutoff region. Cutoff region means what? If both the emitter junction and collector junction are reverse biased. See here in this common base configuration, what is the connection here? Input is forward biased, output is reverse biased. So this type of connection is known as a active region. But here I'm talking about the cutoff region. Cutoff region means what? The collector junction and emitter junction both must be under reverse bias condition. But actually physically it is connected under reverse bias. So what we are doing here, if you make I 0, so that no charge carriers will flow through the BJT. So initially you are not giving any supply. Usually no current will flows under two conditions. If you don't give supply or if it is connected in reverse bias condition. So reverse bias is not possible. Therefore, if you apply I is equal to 0, then automatically IC is equal to 0. That is known as a cutoff region. So if you see here, IE is equal to 0 and IC is automatically equal to 0, this particular area, see, this particular area is known as a cutoff region. So already collector junction is reverse biased. From the input side, you are making IE is equal to 0. That is a operating region is known as a cutoff region. Next, let us discuss a saturation region. Okay, what is meant by saturation region here? Saturation means both emitter junction and collector junction must be under forward bias condition. Already this is under forward bias condition and this is under reverse bias. How to bring this condition into forward bias condition? Less reverse bias means positive. Suppose initially the reverse voltage is minus 20. Then it is increased to minus 30. Then it increased to minus 40. If you reduce the reverse bias, that can be considered as the positive. Therefore, if you see the graph, this is VCB negative, VCB positive towards this side. So, VCB is considered as positive towards the left side of this graph. And already emitter junction is a forward biased. Therefore, this particular region is known as a saturation region. So negative, already VCB is negative, negative of negative will become positive. So the positive VCB and so automatically the collector current, this is known as a saturation region. Because here the emitter junction is already under forward bias condition, you are making this connection less negative. So we are considering it as a positive. Okay. Then another important region is a active region. So the region, the space between the cutoff region and saturation region is known as active region. If you want to amplify BJT as an amplifier or for any signals, the default operating region is active region. So what is the active region here? The active region is nothing but the normal connection. Emitter junction forward, collector junction reverse bias. It's already existing experimental setup. That's why we call this as a active region. So if you want to amplify, it must be connected in a active region. That is a normal default operating region. So the question will be like this. Draw the characteristics of BJT, experimental setup of BJT under common base configuration and discuss input and output characteristics. So these are input characteristics and these are output characteristics. So on the output characteristics, you have to mark these three operating regions. Now, what is the conclusion? After studying this common base configuration, what are the conclusions? So overall, on the characteristics you can study. So the overall conclusion is from this common base configuration, see, a low input impedance and a high output impedance. So this is the first important point you should know from common base configurations is common base configuration exhibit a very, very low input resistance. Very low means, for example, around 22 ohms. Very, very low input resistance and a very, very high output resistance of around 2 mega ohms. One of the important advantages of common base configuration is it exhibits a very low input impedance and a very high output impedance, okay, which is a basic requirement for amplification. Therefore, common base configuration has a highest voltage gain among all the three configurations because of this resistance characteristics. Next, the voltage gain is a very, very high. This is another important advantage of common base configuration, but one of the disadvantage of this is the current gain is low. Why the current gain is low? In case of common base configuration, the collector is the output and emitter acts as input. Whatever carrier starting from the emitter must reach the collector. If it is an ideal transistor, IE must be equal to IC. If IE is equal to IC, this is emitter current and this is the collector current. So what is the current gain here? Collector current by emitter current. If IE is equal to IC, current gain is approximately equal to 1 only. Current gain is 1. But in coming to practical cases, some recombinations takes place in the base. So IC is less than IE. Therefore, it is approximately equal to 1 also. Therefore, one of the drawbacks of common base configuration is the current gain is low, but voltage gain is very high. Input resistance is very low. Output resistance is very, very large. The other salient feature of this configuration is that the input and output are in phase. What do you mean by in phase? So, suppose here through this emitter, I am giving the input a signal like this. So, the output is also in phase. That is here, this is input signal. After amplification, the output signal is, of course it is amplified, but they are in phase. That is the same like this. Okay, so this is an input signal and this is output signal. So how many points we can conclude here? Depending upon the resistors, we can point number 1, and the voltage gain is very high. This is current gain is very, very less compared to all the other configurations, and the input and output signals are in phase. Okay, then next we will discuss about the common emitter configuration. Today we are going to discuss about the another configuration, common emitter configuration. So what do you mean by common emitter? Common emitter means the emitter may be common to any supply or emitter may be grounded. See here, this is a common emitter configuration with the PNP transistor. PNP means the arrowhead point inverse. So this is emitter terminal, base terminal, and this is a collector terminal. Okay, so emitter is common. That is here, this is a emitter may be grounded or may be connected to any supply. Similarly, if you see NPN transistor, the arrowhead point outwards. So this is regarding emitter terminal, base terminal, and this is a collector terminal. Okay, now both transistors are again connected in active region. Active region means between emitter and base forward bias, because this is a PNP transistor. This is a PNP transistor. So P positive, N negative. So this is perfectly under forward bias condition. Collector junction reverse bias. Reverse bias means to the P material minus. So this is under reverse bias condition. So if emitter base is forward biased and collector junction is reverse biased, this is known as active region. Similarly, in this also, this is a NPN transistor. So again, between P and N, forward bias, that is between base and emitter, forward bias, and towards collector, reverse bias. So this is under reverse bias condition, this is under forward bias condition. Both transistors, both PNP and NPN are connected under active region. Now, the characteristics. So what is meant by characteristics? There are two types of characteristics of CE. One is input characteristics and another one is output characteristics. Input characteristics means to draw the graphs by taking voltage and current on x-axis, keeping output voltage constant. Now, let us see the experimental setup of a common emitter configuration.